This video explains a group project done for a heat and mass class at Colorado School of Mines. The purpose behind this project is to compare an analytical transient or unsteady state fin solution to experimental data collected, and that is used to determine the heat transfer coefficient. By modeling the rod as a thin cylindrical nickel rod, this provides simple geometry and known high thermal conductivity. Then the temperature along the rod were measured over time with and without the fan blowing air to calculate the heat transfer coefficient. The table below displays the properties of the nickel rod used. In general, fins are useful for controlling the heat transfer in many different industries like substation transformers, car radiators, heat exchangers, computers, and power stations. The geometry and temperature distribution of the fin can help control the amount of heat transfer with the fin, like in the engine of cars and motorcycles, where more surface area provided by the fin leads to a stable temperature and higher performance. For the setup of this experiment, the rod is approximately 20 centimeters in length, so we divided it into 4 equidistant points and marked them in Sharpie as shown in this top right figure. The rod was fixed to an elevated surface using rubber tongs and tape. Then we allowed the rod to reach equilibrium with the ambient conditions. The outer surface of the jacket was made of an insulating plastic layer, which basically just helps maintain a fixed temperature. Ice was packed into the external chamber of the jacket, and the internal jacket was filled with cold water. To check the temperature of the fin, we used an infrared thermometer of the fin to check the temperature of the fin and water until they were relatively constant, meaning that the system is at steady state. The 2 cases tested for the temperature data were with and without the fin, and we collected data upon that. The main results basically these 2 tables show multiple trials with and without the fan present, where temperature was measured every 4 minutes at the 4 different points across the rod, along with the temperature of the air and water. By solving an unsteady state temperature profile, we can get to an expression for temperature as a function of position and time. After this, the data collected can be used for data fit with the analytical solution to find the heat transfer coefficient for both cases. So there are some ways to improve this experiment, and there's also some sources of error. So overall, the value of the heat transfer coefficient for air, which is H, is dependent upon several factors like the geometry of the surface experiencing convection, the type of fluid motion, the fluid properties, and the velocity of the fluid. Fluctuating variables in the ambient conditions also may have been the source of several errors. The temperature of this room fluctuated due to the outside temperature decreasing and also the house furnace increasing the inside temperature. The velocity of the air that was measured likely also changed from the velocity during the actual experiment, and the velocity of the air during the experiment likely fluctuated over time due to inconsistent air flow from the fan and movement around the project. Along with this, the assumption of an adiabatic fin tip may have also introduced errors into the analysis. A more accurate value of H may be determined if the experimental conditions were consistent. So doing this experiment during a time of day where the temperature is steadier, or in an environment where the conditions are better regulated, may increase the accuracy. Lastly, having a different person measure the temperature across the various positions of the rod over time can lead to a slight error due to the timing and different measurements technique. A way to minimize this error is to have the same person with the stopwatch timing all the trowels and the same person measuring the temperature of the rod to allow consistency in the measurements. Thank you for watching this presentation and see you next time. Thank you.